let's say I have some subspace of Rn called V. Let me draw it like this. So that is Rn. That is Rn. I have some subspace of it that we'll call V right here. So that is my subspace V. We know that the orthogonal complement of V, is equal to the set of all of the members of Rn, all of the members of Rn. So x is a member of Rn, such that x dot v is equal to 0 for every v that is a member of our subspace. So our orthogonal complement of our subspace is literally all of the vectors that are orthogonal to all of these vectors. And we've seen before that they only overlap. There's only one vector that's a member of both, and that's the 0 vector. Let's say it's right there. And let's say the orthogonal complement, let's say it's this set right here in pink. So that's the orthogonal complement. Fair enough. Now, what if we were to think about the orthogonal complement of the orthogonal complement? So we want the orthogonal complement. So that's the orthogonal complement. That's the thing in pink. But we want the orthogonal complement of that. So this is going to be all of the x's. Let's just write it like this. All of the x's that are members of Rn such that x dot, let me just say, x dot w is equal to 0 for every w that is a member of the orthogonal complement of V. That's what that thing is saying. So it's all of the vectors in Rn that are orthogonal to everything here. Now, we can think, obviously, all of the things in V are going to be a member of that because these guys are orthogonal to everything in these guys. But maybe this is just a subset of the orthogonal complement of the orthogonal complement. So maybe this thing in blue right here looks like this. Maybe it's a slightly larger set than V. Maybe there are some things, these things that I'm shading in blue, maybe there are some vectors that are orthogonal to the orthogonal complement of V, but that are outside of V. We don't know that yet. We don't know yet. We don't know whether this area right here exists, or maybe the orthogonal complement of the orthogonal complement, maybe that takes us back to V. Maybe it's like the transpose or an inverse function, where it just goes back to our original subspace. So let's see if we can think about that a little bit better. So let's say that I have some member of the orthogonal complement of the orthogonal complement. So let's say I have some vector x that is a member of the orthogonal complement of the orthogonal complement. Now, we saw in the last video that any vector in Rn can be represented by a sum of some vector in a subspace and the subspace's complement. So we know that x can be represented. We can say that x can be represented as a sum of two vectors, one that's in V and one that's in the orthogonal complement of V. So let's call that the vector that's in V, and let's call W the vector that's in the orthogonal complement of V. Let me write it like this. Where V is a member of the subspace V, and the vector W is a member of the orthogonal complement of V, right? So this is some member. It could be some guy out here. It could be some guy over here. He's a member of the orthogonal complement of the orthogonal complement, which is this whole area here, which V is a subset of, but we're not sure whether V equals that thing. But we say, look, anything that's in the orthogonal complement of the orthogonal complement is going to be a member of Rn, and anything in Rn can be represented as a sum of a vector in V and a vector in the orthogonal complement of V. So that's all I wrote right there. Now, what happens if I take the dot product of x with W? What is this going to be equal to? Well, this is the orthogonal complement of the orthogonal complement. So if you take the dot product of any vector in this with any vector in the orthogonal complement, which this vector is, right? It's a member of the orthogonal complement, you're going to get 0 by definition. These are all of the vectors. This vector is definitely orthogonal to anything in just V perp, right? Anything in V perp is orthogonal to anything in V perp. So this thing is going to be equal to 0. But what's another way of writing x dot w? We could write it like this. This is the same thing as v plus w dot w, which is the same thing as v dot w plus w dot w. Now, what is v dot w? V is a member of our original subspace. And if you take the dot product of anything in our original subspace with anything in its orthogonal complement, you're going to get 0. So this term right here is going to be 0, and you're just going to get this term, which is the same thing as the length of our vector w squared. Now, that has to equal 0. Remember, we just wrote x dot w. X is a member of the orthogonal complement of the orthogonal complement. So you dot that with anything in the orthogonal complement, that's got to be equal 0. But if we write it the other way, if we write it as the sum of v plus w and distribute this w, we say that's the same thing as the magnitude of w squared. So the magnitude of w squared has got to be equal to 0. The magnitude of w squared, or the length of w squared, has got to be equal to 0, which tells us that w is the 0 vector. That's the only vector in Rn that when you take its length, and especially when you square it, you get 0, but you could just take its length. So what does that mean? That means that our original vector x is equal to v plus w, but w is just equal to 0. So that implies that our original vector x is equal to v. And v is a member of our subspace v, right? So that tells us that x is a member of our subspace v. So what we just showed that if something is a member of the orthogonal complement of the orthogonal complement, then that same vector has to be a member of the original subspace. So there is no such thing as something being in the orthogonal complement of the orthogonal complement and not being a member of our original subspace. All of this has to be inside of this right there. So there is no outside blue space like that. All of that is our original subspace, if you want to view it that way. Now, I just, at the beginning of this video, said, hey, anything in our subspace is going to be a member of our orthogonal complement, and you can kind of reason that in your head. But let's use the same argument to just be a little bit more rigorous about it. So let's say right now we say, look, if anything is in the orthogonal complement of the orthogonal complement, then it's going to be in the original subspace. Now let's go the other way. Let's say that something is in the original subspace. Just like that. If anything, let me draw another graph right here, because this might be useful. Let me draw Rn again. Let me draw all of Rn like that. Now we have the orthogonal complement. Let me just draw that first. So v perp, and then you have the orthogonal complement of the orthogonal complement, which could be this set right here, right? This is v perp. I haven't even drawn the subspace v. All I've shown is I have some subspace here, which I happen to call v perp, and then I have the orthogonal complement of that subspace. So this means that anything in Rn can be represented as a sum of a vector that's here and a vector that's here. So if I say that w, let me do it in purple. If I say that the vector w, or let me write it this way, the vector v can be represented as a sum of the vector w and the vector x, where w is a member of the orthogonal complement of v, or v perp, and x is a member of its orthogonal complement. Notice, all I'm saying, I could have called this set S, and then this would have been S and its orthogonal complement. And we learned that anything in Rn can be represented as a sum of something in a subspace and the subspace's orthogonal complement. So it doesn't matter that V is somehow related to this. It can be represented as a sum of a vector here plus a vector there. Fair enough. Now, what happens if I dot V if I dot v with w? I'm doing the exact same argument that I did before. Well, if you take anything that's a member of our original subspace and you dot it with anything in its orthogonal complement, that's going to give us 0. What else is that going to be equal to? Well, if we write v in this way, v dot w is the same thing as this thing dot w. So w plus x dot w, and this is going to be equal to w dot w plus x dot w. And then what's x dot w? X is in the orthogonal complement of the orthogonal complement, and w is in the orthogonal complement. So if you take their dot product, you're going to get 0. They're orthogonal to each other. So this is just equal to w dot w, or the length of w squared. And since that has to equal 0, right, we just have a bunch of equals here, that tells us that, once again, the vector w has to be equal to 0, and that v, so that tells us v is equal to w plus x. But if w is equal to 0, then v is going to be equal to x. So we've just shown that if v is a member of the subspace V, then V is a member of the orthogonal complement of the orthogonal complement, right? V is equal to x, which is a member of the orthogonal complement of the orthogonal complement. So we've proven it both. We've proved it both ways. If you look at the original statement, we wrote here that if you're a member of the orthogonal complement of the orthogonal complement, you're a member of the original subspace. So we proved this, and earlier in the video we proved that if x is a member of the orthogonal complement of the orthogonal complement, then x is a member of our subspace. So these two things are equivalent. Anything that's in the subspace is a member of V perp perp. Anything in V perp perp is a member of our subspace. So our subspace and V perp perp are the same set. And of course it overlaps. This equals this. And of course it overlaps with V perp, its orthogonal complement, only at the 0 vector right there.